Next presenter is Andrew Hinton from Digital Science. He joined Digital Science team as a chem informatics developer for SureChem. He's responsible there for ensuring quality and consistency of the data content. He previously worked as a computational chemist for Merck. He gained his PhD in chemical information from the University of Edinburgh in 2005 and holds an MSc in molecular biology. Well, that's going to be interesting. In his spare time, he enjoys gardening, canal boating, and real ale, which I do too myself. And he's going to talk about structural normalization in chemical extraction from patents.
I'm Andrew, and I work for Digital Science, which is a business unit of Macmillan Publishers. I work particularly in the SureChem patent chemistry mining software technology unit, and I'm going to be sort of presenting today about the technology, specifically ChemAxons technology that we use in our SureChem Open software product. This is essentially a patent chemistry mining piece of technology that automatically extracts chemistry from the text of a patent as well as clipped images, and we take the chemistry from all major patent issuing authorities. So this is our, briefly, this is our interface that we have, and under the hood it's powered by JChem-based technology that provides a integrated interface to search the bibliographic and full text of the patent. This allows you to visualize the chemistry from the text in line as you navigate through the patent, as well as seeing the extracted chemistry from the clipped images as you go. So just in a bit more detail, what I want to walk you through now is our workflow. We've recently moved to an infrastructure that's hosted on AWS's Amazon's web service, cloud-based infrastructure, and we're able to take patents issued from the IFI Fairview, which is an integrated federated patent provider, and we can take the XML of the different authorities as well as the clipped images, and we pass that into our SureChem's own proprietary entity recognition extraction software, where along with our sort of in-house OCR heuristics and some commercially available, I see Roger's in the audience here, we're able to correct for the OCR mistakes, the spelling mistakes, the white space that often corrupt chemical names, such that when we then have a list of chemical entities, we're able then to pass them on to a suite of name-to-structure tools, two of which I can tell you about their Opsin, but also we use ChemAxon's own name-to-structure conversion tool. So that's the chemistry that we get from the names, but we also then process the chemistry we find in the clipped images coming from the patent authorities, and we use Key Modules Clyde software to do image-to-structure recognition. But what I want to focus on today is how we then use ChemAxon's Standardizer and Structure Checker to handle the molecular entities coming from either the name-to-structure or image-to-structure recognition, and the filtering and the transformation that happens at that stage before ultimately we register the compounds, again using some ChemAxon JChem technology to provide the search that users can utilize on the interface. So this is one young artist's visual interpretation of chemical noise, and we get a lot of chemical noise coming from the image to structure and name to structure process. And you know, we often hear from our users that chemical noise is a real problem, but they rarely define it in any full extent. So it's a very subjective term, but broadly speaking, we think of it as sort of irrelevant chemistry that, at best may just hinder a user's ability to find the correct chemistry they're looking for, but at worst can seriously delay or sometimes absolutely prevent the user trying to actually get to the relevant chemistry within a patent because they're subjected to so much uninteresting, irrelevant chemical noise going around it. And other than the sort of increasing the haystack issue, the problems associated with chemical noise and irrelevant chemistry can also take a different form in such that the misrepresentation due to the ambiguous nature of chemical representation in 2D or 3D can actually prevent a user walking through a chemical landscape due to the fact that the misrepresentation of chemistry actually prevents the linking from the SureChem database out into, say, ChemSpider or PubChem, and actually the movement is hindered. To give you some sort of examples of what we're talking about that we often find in chemistry, it'll either be sort of annoying variations in the sort of the names, the abbreviations, or when it comes to actually the representation of the chemistry, charge groups, stereo and tautomeric isoforms will either vary in nature or just be misrepresented or completely absent. There is, unnecessary chemistry is also present in a patent where common simple elements will be extracted and shown to the user, again increasing the noise level. Ambiguous groups. There are also quite serious issues with nuisance fragments that specifically arise from the name to structure or image to structure process, whereby we can recognize Marcouche elements, but they actually have no context. They may just have partial name recognition, whereby we've encountered some white space, and this is actually artificially truncated a chemical name which has generated unlikely chemical species. So these are all fairly serious misinformation that we can do without. So what we've employed is a robust structure handling system which utilizes the features in Structure Checker and Standardizer, whereby we're really using the power that we can see using smirks to transform molecules into a better standard form. We're able to filter and remove, detect chemical entities that are either empty or erroneous, have some sort of erroneous atom type. And we can take into account differences in aromaticity, charge, and accounting for hydrogens. So if you're familiar at all with these two products, you'll be aware that they actually have quite a nice GUI available to them. And we used the GUI in the initial development phase of constructing the normalization workflow. We ultimately, in production, we used the Java API implementation of Structure Checker and Standardizer. And we found that what we needed to do was utilize it at several different points, specifically the image to structure and name to structure processes, and also immediately before we store and search the chemistry, we need to apply some sort of structure handling at this point. But mostly it was all to do with filtering and transforming a structure, specifically, as I said, from the image to structures. A lot of the noise was removed from this. Ultimately, what we hope is we will see fewer duplicates stored once the changes have taken place. Having gone through that, we're able to, having put it in place and run a series of patents through our workflow as a whole, we're able to do some sampling. And the top transformations shown on this slide here come from about 1,000 structures. And we can see that of the 1,000 structures, some of the top transformations that these structures underwent were mostly in the areas of handling of charge, expanding, and dealing with abbreviations and expanding aliases. There's also some dealing with aromaticity as well there. But perhaps a more palpable way of judging an improvement is by looking at and inspecting particular patents by eye. This on the right-hand side is a single clipped image from a US patent, and on the left-hand side nearest me, we can see the molecules extracted from this clipped image, and we're able to see that what we want to do is we want to actually retain the structures at the top, but we want to perhaps move some of the artifacts that are actually arrows and will often creep into the image to structure recognition from our list of chemicals. We can see that actually we do this. We're able to, at the same time, to deal with wedge bonds. We're able to deal with structures that are actually have problems with the structure somehow, and that are unable through the process to be reconciled, and we're able actually to remove these, and we're also able to deal with protecting groups and simple issues of chemical nomenclature and shorthand. So, just to wrap up, some of the to summarise and sort of give a little critique here, the positives, we found the GUI was really easy to use, and actually that was translated when we came to implement the routine that we had developed at a Java API level. The two products provide most of the functionality that we required, and there were enough, if not limited, examples of best practice available on the ChemAxon website to guide us. Some of the negatives were such as error handling. It was a little bit flaky. We had lots of crashes at the beginning, but when we understood, when we got to sort of grips with it, those errors tended to become fewer and fewer. So one of the issues that we did come across was the tautomerization that is available on Standardizer, I think it is. That really wasn't, we found it really wasn't suitable for unguided automated use. It tended to have a very high, as you can imagine, time impact, and that when you're actually potentially giving molecules of all different shapes and sizes, there was a lot of inappropriate tautomerization going through there. So we will look at implementing better use of tautomerization, but it's going to take a while to develop better filters, I think. The final point is that the documentation is quite good, but the two products do overlap, in my mind, a lot between each other. And so the overlap does provide a challenge when first reading it, because you really want to be able to distinguish which tool the different features provide, and there's quite a bit of overlap. So with that, I think, any questions? Yeah, I'll take any questions.
Just a short question. How do you recognize the artifacts you mentioned, these arrows in your molecular stuff?
That's a very good question. We had to use sort of fairly esoteric principles in there. So basically, if something tends to be, if it's all carbon, will be an issue. So and they tend to have quite strange properties that you wouldn't expect a molecule to have. It isn't foolproof recognizing these artifacts, but they tend to be that if a molecule is all carbon and doesn't have any other atom types, we tend to treat that as suspicious, and we remove it. But again, it's not a very nice way of doing it, because you obviously run into issues with alkanes and alkenes and such like. So yeah.
Have you tried we have a checker for that, similar way?
Yeah, I'd like to catch up with you and explore that, because yeah, it's not a foolproof method at the moment.
Okay.
Thank you.
Okay. Thank the presenter again.